Yeah, very good. And I should maybe copy this graph so I don't have to redraw it. Okay, so I don't want to spend too long on these because, again, these are from last week, and I do kind of want to get to some of this week's stuff. So I might call these just a little bit quicker than I normally would. So I'm going to give you about a minute left, though. Okay, so because there isn't anything to really compute here, right? You just look at the graph. So let's say, down to 45 seconds now or so. Jeremiah, no, actually, no, that's not. I've never been much into watching it, but like I used to play it as a kid. I played till I was probably 17 or 18 years old. But I mean, it's been, 18 years since then. So I'm certain I've lost any skill that I had. All right, 10 seconds. Just over half of you have voted. I want to get some people in here. Guess even if you don't know, right? Just get an answer in. Okay, let's take a look at this. That's pretty even, right? That's like, again, sort of saying maybe that the class doesn't know. So again, this was a test question, right? And fully legitimately the sort of thing that could come up. So let's figure out what's going on here and how we would have solved this. Why couldn't you do that? I'm now very upset with you, Windows. What is going on? Please try copying and pasting again. Paste. Okay, we're going to try this one more time. And if this doesn't work, I'm just going to draw the bloody thing. Okay, right? All right, damn it. Well, you know what it looks like. All right, let me just draw it roughly. What do we've got? So we got like -1, -2, -3, 1, 2, 3. I was hoping not to waste time having to do this, but stupid Windows. And then we've kind of got this half circle here. And then we go up again. And then 1 to 2. And then we go whoop, way down like this. Okay, so the graph looks something like this. No, that's why you work with Linux. 100%, always Linux. Anyway, so this is our graph. This is f of x, right? This is the function f of x. And then we're told that we've got this function. What do we say? What do we call it? H of x, which was the integral from -3 to x f of s ds like that. Okay. So i.e. we're looking for the area under the graph of this function, right? That's what this function is doing. So h of 1, for example, would be the area from -3 to 1. Now, turns out most of that, like all the things here, are relatively straightforward enough that we can actually compute the area under the graph, but the point is you don't have to. Because the question asks, on which intervals is h increasing, right? So where is h increasing, right? And if you remember sort of like your derivative stuff and the fundamental theorem of calculus, you can determine where a function is increasing by looking at the sign of its derivative, right? So let's look at h prime. So we can say something like, well, h prime of x is equal to f of x by the FTC. Right? And so h will be increasing wherever f of x is greater than 0. All right, so we want to look where is, so h prime of x will be greater than 0 whenever f of x is greater than 0. And if we look at our graph here, that looks like it's probably this thing and this thing right here, right? So what is this? This is like -3, this is -1, this is 1, and this is like what, 5 halves? So we're going to take the union of those two intervals, -3, -1, union 1, 5 halves. There's our answer. And that was option D, like that. Okay, does that make sense? Any questions about that? Why do we use the FTC? So I'm trying to figure out the derivative of capital H, right? Because remember, how do we check if a function is increasing or decreasing? We look at its derivative, right? So I need to compute the derivative of this function. So what is the derivative of h of x? Well, that's the derivative f of s ds. And the fundamental theorem tells us that like the derivative and the integral cancel each other out, right? That's what the FTC tells us. It does. And Connie, let me talk about that in a second too. But yeah, let's make sure that we understand like what I did here. And then maybe I can talk a little bit about more of the intuition behind how would we guess this if we didn't know the FTC, right? Simon, I don't remember exactly which one is FTC 1 and FTC 2. Mathematicians, they're both just the FTC, right? And Brandon, yeah, absolutely. That is another way of thinking about it. So the other way of thinking about this is to just to say intuitively, again, remember the area under the graph of the function, but it's signed, right? So area above the x-axis is positive and area beneath the x-axis is negative. So again, if you think about this function, it's going to be increasing wherever it's adding area, and it's going to be decreasing wherever it's subtracting area. So as long as your function is above the x-axis, then what that means is that as the area as you move along the x-axis and compute the area under the curve, that you'll be adding area as long as your function is above the x-axis, and you'll be subtracting area as long as the area is, or the graph is beneath the x-axis, right? So you can think about it like that instead if you don't really want to use the FTC. But if you were asked to provide some sort of justification, you'd either have to write that out in words, or you can use the FTC like this. So Connie, does this make sense about like, here's me using the FTC, right? And I used that like there, right there. Okay, cool. So yeah, this is, this problem is an example of the fundamental theorem. So there's a second part to this question. So based off of what I just said, I hope that you all are able to now do this question. So it's the exact same graph, right? All right, having trouble clicking the button. Okay, so now I'm asking where are the critical points, right? So think about it, exactly what we just said. Where are the critical points? Terrace, there's no capital F. And then if you have an X on the left and an S on the right, that's a little bit weird. So I'm not 100% certain what you're asking. Yeah, Connie, that's fine. Yeah, right. That's exactly what the FTC tells you. So that is okay. Yes, yeah, capital H is an antiderivative of little f, and that is the other part of the fundamental theorem. Yeah. So when you take the derivative of an integral, it becomes the function. Yes, generally that is the fundamental theorem, but you have to be a little bit careful, right? Because when you do that, here, let me annotate this. So it's really important that that x here is just an x, right? If this is some other function, then you have to do one of the things that we did last Tuesday, where you have to write this as like a composition of functions and then differentiate using the chain rule. So here, everything's totally okay. We're just using an x in the upper bound of integration. And so we can use the FTC directly. This is a good question. So I got asked, only the upper bound. So for the FTC, first of all, you don't care about what the lower bound is. It could be any number, but it has to be a number, right? So it can't be like an X or have a function in it. So it could be 7, -pi, whatever you want. Now, if the bottom function or if the bottom bound does have a function in it, like it is an X or something along those lines, you have to, exactly. You can use this additivity of domain property. Another thing that you could do is if there's an X just in the bottom and there's a number in top, remember, if you take the negative of that, you can flip the bounds around, right? You can move the bounds around just by taking a negative sign of the integral. So you can do it that way. You look at what we did last Tuesday. I think I actually did do an example where there was a function in the lower bound, and I explained sort of a bunch of the different ways that we could account for that there. So you can check that out. And then, yeah, if you still have any questions, let me know. I'm going to lock this up in like 10 seconds here. So everybody get your answers in. It's looking pretty good, though. I think most people have it. The negative part? Oh, yeah, sure. Let me write something down. Let me finish the polls, and then I can say something quickly there. Okay, so most of the class said C, which is phenomenal because C is absolutely the correct answer. So again, sort of let me copy. I wonder if it's even going to let me copy this. Where's my mouse? Here, let's see if it lets me copy this graph. Copy, paste. Okay, so why does it work here? I can't. I don't understand. Why are you here? Delete you. Go away. Okay. So here's our graph again. And just like last time, right? So we had h of x is the integral from -3 to x, f of s ds. So the FTC tells us h prime of x is f of x, right? That's what the FTC says. Now remember, critical points are where the derivative is equal to 0 or fails to exist. So if we look at this, we want the critical points of h. So we want this to be equal to 0, right? So I'm going to look for where is the graph of f of x equal to 0. And the answer is right here, right here, and right here. And this is -1, 1, and 5/2. And so that is C. Right? Now, there were a good chunk of people who said B. B would be the correct answers if I were asking you for the critical points of the function f, but I'm not, right? I'm asking for the critical points of the function h, not f, right? What about f of 3? I mean, so, well, you don't want to take like negative, you don't want to take the value of the function, right? So you don't want to look at f of -3, but are you asking like, what about -3? You could probably make, I'm not certain what you're doing. Yeah, I'm not quite certain what you mean. Like, where's the f of x minus f of -3 coming in? So I think what you've done, you've maybe done something here where you're like, okay, So the integral from -3 to x, like you've chosen some sort of antiderivative and you've written this as like f of x minus f of -3, right? And then you still have to differentiate this. And when you differentiate, you would just get f prime of x. But by definition, capital F was the antiderivative of little f, right? So you would still just get little f of x. Okay, yeah, that clears it up. And Jeremiah, so what's on the screen here? This graph is just of little f, and h is the function which integrates it, right? This is the definition of h. So for example, if I asked you for h of -1, that would be the integral from -3 to -1 of this function, and that would be this area here, right? And that's how you would compute it, is you'd actually compute the area from -3 to -1, right? Here, maybe let me make this green so that we can see that. And then if I, oops, that's green. Damn it. Green. Okay. Fine. I will make you red instead if you're going to be like that. And if we had done something else, excuse me, if we had done something else, like say I had done h of 2, that would be the integral from -3 to 2 f of s ds. And that would be that would look like this, right? So the way that you actually compute the integral is, or the function h, is by computing the area under the curve up until the point that you're specified. Okay, so I was asked, like, what does it mean? Like, you know, I mentioned something about finding the critical points of the function f versus the function h, right? So let me put these in black. These black points here, and actually, for those of you who maybe did it, you missed a bunch. So these black points are the critical points of the function little f. Okay, because it's anywhere, and actually, yeah, this is also all, these are also all critical points. So everything in black is a critical point of little f, but that's not what we were asked, right? The question asked, what are the critical points of capital H? And capital H is the integral function. So if we use the fundamental theorem of calculus, the critical points are those blue things, right? They're wherever the function is equal to 0, i.e. the critical points of the integral are the same thing as the roots of the integrand. Oh yeah, you're right, thank you. X equals 0 is also a critical point of the original function. Thank you, Owen. Okay, everyone? Now there's a third part of this question, which I'm not necessarily going to do, but I want you to try on your own now. You've got candidates for the critical points of capital H, right? We said it's -1, 1, and 5/2. I want you to classify each of those critical points. Are they inflection points? Are they minima? Are they maxima? Okay, use the first derivative test or the second derivative test, whatever you want, but tell me, are those maxima or are those minima? Okay, and you can try that as sort of a bonus thing. I'm going to move over into this week's poll questions, but if you want to work out, like, you know, answer this week's poll questions, but if you finish them and you've got a little bit of time, see if you can figure this one out and determine what the maxima and minima are. Okay, that's a really good example. Okay, so let me switch over to this week. And which one do I want to do? This is question 1. Yeah, we should probably just start here, right? Let's start with like a relatively straightforward one. Okay, yeah, that's an interesting question. So the purpose of the numeracy stuff is, so the numeracy stuff is stuff that you should have learned in high school. But we know that some students come in and they're just like, oh man, I've totally forgotten a bunch of the stuff that I learned in high school, or it's just been a long time, or you went to high school during a pandemic, right? And different people are really at different places in terms of their numeracy. So what the numeracy is designed to do is to get you acquainted or perhaps reacquainted with the materials that we're going to use. So for example, assignment, whatever it is, 11 is this current assignment, is a numeracy assignment. You'll actually notice there are 3 numeracy components. Those things are all things that we are going to use in the upcoming 3 weeks, i.e. they're all stuff that we're going to use for multivariate calculus, right? And you probably noticed that if you've looked at the assignment, you'll notice one exercise has you working a lot with functions of multiple variables, which is something you may have not even ever have done in high school, but we would just want you to get a little bit familiar with playing around with these functions because that's what we're going to do. So starting with that, one has you solving nonlinear systems of equations, right? Linear algebra is about solving linear systems of equations, but what about nonlinear things? We're going to do that a bunch too. And then what was the last thing? The last thing is like writing spaces kind of like this, right? Where you kind of like bound it by a function above and a function below. And that's because we're going to talk about multivariable integrals as well. So it's all about just figuring out these things. They're not strictly speaking within the scope of this course. It's about getting some exposure to them because we're going to use these things when we get into the multivariate calc. No, so I've got a direct message saying, I never learned any of this in high school. Does that mean I'm screwed? No, definitely not. Like this is an opportunity for you to learn them and not have to learn them on the fly. You know what I mean? Like you're doing it as part of an assignment. So you get to figure some of this stuff out before we also throw calculus on top of it. Like imagine if you had to figure all this stuff out and then we're also doing calculus with it. I think that's probably a lot for some of you. You kind of get overwhelmed. So if we can even just give you the numeracy portion first, sure. Yeah. I mean, if it helped, but like if, we give the numeracy to you first and you have an opportunity to sort of play with it on your own and get comfortable with it. And then we throw the calculus in, the hope is that you'll be able to make that transition a little bit better. Okay. I'm going to cut this in 30 seconds. Because again, there isn't anything to do. You just, know what the answer is if you do, and you don't if you don't. But yeah, no, this is great. Like overwhelming majority of the class sort of has the answer here. But I realize, okay, what are the chances that it lets, no, it's not going to let me copy and paste because it's a jerk like that. Ooh, okay, I have to remember what the thing looks like. No, there are no inflections. I recommend using the first derivative test, right? Like think about how when we did the first problem, we said this is what it means to be increasing and this is what it means to be decreasing. Do you know what I mean? So look at, for example, -1 as a critical point and say, is my function increasing to the left or is it decreasing to the left? Like you tell me, and then I'm gonna start to take this one up. And yeah, this is great. Like overwhelmingly, the class said B. B is totally the correct answer. Yeah, damn it, I'm gonna have to draw this thing again. All right, so we've got like one function like this, one function like this. Here's g of x, and here's h of x. And we're after this thing. And totally, like even if you think about what the lengths of any one of those lines is, the length of those lines is precisely g of x minus h of x. And if you think about the integral as sort of like sweeping from left to right in order to calculate the area, that gives us exactly, the top function minus the bottom function. Should be increasing to the left of -1. Right? Because the function is above 0, if I recall correctly. Right? Okay, so yeah, so this is then the difference between the upper and lower bounds. Why is my pen not working? Damn it. G of x is the top line, right? It's the top curve. Let me see, I might just need a new battery here. stupid pen. Okay, this better work. Ooh, I think you might have those backwards, Emma. Except for 5/2. I think that's, let me double check. All right, CSZs. Okay, hold on. Let's see if my pen works. Okay, woo, my pen is working. Okay, so the answer to this one is g of x minus h of x dx, whatever our bounds are, right? Here's a, here's b, like that. Okay. Oh, we called them C and D or whatever. So this is the answer. This was answer B. Okay, so I mean, a bunch of people are asking about the kind of bonus question I gave in the previous one. We'll go back to that one in a second. I just want to make sure, is everyone comfortable with this? Is like anyone need me to go more on this one? So Jeremiah, you're talking about this one or the other one? Right, okay, so here, maybe let's think about it like this. Because, you know, you're right, totally. If you memorize it, that's one thing. Let's say I gave you just straight lines, right? Like, let's say I gave you the f of x equals 2 and g of x equals 4, right? So I plot these lines. Here's f of x equals 2. Here's g of x equals 4. And I want this area here, right? Like this, let's say this is, you know, what? This is 1 and this is 5, right? Well, okay, so does this make sense? Like the height here is the difference between these two functions. And then I'm going to integrate that from 1 to 5, right? Yeah, okay, so now, like, does it make a big difference if I change it? So instead of being a rectangle, right? Like I choose two different functions. So now I've got like g of x looks like this, and h of x looks like this. And I'm after this area, right? So what I'm going to do is I'm just going to take the area under g of x here. Maybe let me even kind of draw. What is the integral under g of x? It looks like this, right? And now I'm going to subtract the area under h of x. So maybe h of x is the blue curve. Okay, so I'm going to subtract the area under the blue curve. And what's left over? Well, the stuff left over is the area I was looking for, right? So does that make sense? So if I want this stuff, there's too many colors here, right? But if I want the yellow stuff now, so I'm going to get the yellow is equal to the green stuff minus the blue stuff, right? And that says to me then that the integral, or so the yellow stuff, that's the stuff that I'm after, is equal to the integral of g of x. And I guess we call this C and D, right? So C to D minus the integral from C to D h of x. And if we want, we can just combine both of those things together, right? Like so. So does that help? Does that make sense? Okay, cool. What if the shape becomes 3D? So that is a question for 2 weeks from now, right? Which is like, what do we do when it's 3-dimensional? Oh, you're right, I did. Okay, let me go back. Okay, but let's check first. So everyone's good with this? Everyone's comfortable? Hopefully, yes. Just scream if you're not. Okay, so Chen, don't let me forget, okay? Okay, so a bunch of students are kind of asking about this question. Let me just get rid of all these extraneous marks here. And hopefully I can do it without deleting the graph. Oh no, that one's gonna be too hard. Okay, so we said, here are the critical points, right? There's one at -1, one at 1, and one at 5/2 like this. And so again, I wanna use the first derivative test in order to classify these. So what I wanna do is I wanna look at what is again, capital H, right? What is the function capital H doing around each point? So to the left of -1, is H increasing or decreasing? Like on this interval right here, is H increasing or decreasing? Right, this was the first question that we did, right? This is increasing. Does everyone agree, right? Because the function is, right, perfect, because the function is above 0. Okay, on this interval, what's the function doing? Decreasing, great. Maybe let me just write DC. And then on this interval right here, increasing, great. And then finally on this one, it's decreasing, right? Okay, so if I look at this critical point, I'm increasing to the left and I'm decreasing to the right. That must look like a maximum, right? Because that's what maximums do, right? You're increasing to the left and decreasing to the right. For this critical point, I'm decreasing to the left, increasing to the right. For this critical point, I'm increasing to the left and decreasing to the right. Does that make sense? Is everyone good with that? Right? That's what the first derivative test tells you. And this one would actually be pretty tough to do with concavity. So first derivative test, definitely the way to go with this. I'm going to assume. So an inflection would look like, again, remember you're taking the graph of the, you're taking the area under the graph. So if I had a function that looked like this, right? So that when I'm taking the area under the graph, what is going on, Pen? So where it hits 0 are still critical points, right? But notice that the function stays above 0, both to the left and to the right, i.e. it's increasing to the left and to the right, right? So this function here, we still get critical points here, right? These are critical points, but we're increasing everywhere, right? We're increasing here, we're increasing here, we're increasing here. So this function, if you were to actually graph what the graph of this, like what the integral looks like, it would look something like this, right? And that's how you would get your inflection points showing up. Is that good? Does that make sense? Okay, cool. And then I was reminded that I actually didn't explain to anyone about the FTC and if the x is on the bottom. So for the FTC, so remember the derivative from 0 to x f of t dt, this is f of x. And so the question is, well, what happens if the x is on the bottom? Well, remember that you can flip these by throwing a minus sign in front, right? So this was something I promised I would talk about way back, and I forgot. And so this is what I meant by flipping with a minus sign, right? If the x is on the bottom, okay, I can't differentiate, right? I can't do this using the FTC. It has to be a number at the bottom and x at the top. So if I get that, fine. How do I do it? Well, I'm going to force them to switch. And how do I do that? By throwing a minus sign in front, right? So that's how I fix that. So is that good? For those of you who I promised that question to, that answers it? Cool. That's just the rule. So in order to really show it to you, and I would love to, but I would need to prove the fundamental theorem of calculus for you to see it. And the proof isn't terrible. It's a beautiful, beautiful proof, but it's just not the sort of thing that we would do in this class. You know what I mean? So right now you should just take it to be a rule that the x has to be on the top. You have to have a numerator on the bottom. Yeah. Okay. Yeah, no problem. So, all right, let's step this up in difficulty a little bit. No, I don't want to do that one. All right, let's do a little bit of computation. Let's do something a little bit. Wait, no, this is the wrong one. No, I don't want to do that one. Let's do this one. Straight out computation. Now you can put this into Wolfram Alpha, but I don't want you to. I want you to practice with real numbers, right? Because some of you get upset. So I want you to practice this with real numbers. And of course, you all should get it correct, because then you can go and plug this into Wolfram Alpha, right? Like if you know what you're doing, you can check your answer, but I want you to try to do it without that first. Okay, so give that a shot. Okay, and I'll be right back. Just give me a second here. Sure same. All right, everyone, how's it coming? I think I'm going to lock this. This is a longer computational one, so I don't mind giving you a little bit of time here, but I wanted to take it up. So 15 seconds here. It is. All right, everyone. This is not great. So the correct answer is D. And one person answered D. All right. So something's wrong here, right? Something's off. And again, obviously, if you have to leave and you got to run, just run. You know, we're recording. I'll post the recording. Okay, so we're asked. Let me just kind of give you a rough. Let's look at this function, right? And I'm going to do. Oh shoot, I changed my thing. So it's x cubed minus 3x squared plus 2x, right? That's right. That's right. Okay, so I'm going to factor this x minus 2, x minus 1, like so. Okay. And so again, I have an idea now of what this function looks like. So even if you don't know what this is, I know this is a cubic. So it kind of like, you know, it's going to look like a wave, right? What would you call that? It's a double. It's got, you know, a max, it's got a min, and then otherwise it shoots off to plus or minus infinity. So without knowing exactly what it looks like, I know it goes through 0, I know it goes through 1, and I know it goes through 2. So this thing looks something like this, right? And even if you didn't know this, that's fine. You can still totally do this question without having any idea what this function looks like. Okay, but I think it helps to have a little bit of an idea of what it looks like. And especially since so many people got it wrong, let me draw what we're after. So we're after the absolute area from 1 to 3, right? So if I just asked you for the integral, that would look something like this. But, okay, sure. But in this case, right, remember the integral is assigned area, right? So any area under the x-axis is negative. And when you're asked for the absolute area, this means that now all the area is positive. Okay, so this area under here that is beneath the x-axis, you now have to give it a positive weight. Okay, so that's sort of the important thing. So let's say, here, let me sort of do it properly, and then I'll show you, even if you didn't know what this thing looked like, how could you have solved this problem? And the answer is there's a bunch of ways. So I know that the roots of this function are 0, 1, and 2, right? These are the roots of the function. And I'm asked to integrate the function from 1 to 3. So what I'm trying to do is this thing, right? So x cubed minus 3x squared plus 2x dx. And because I know like roots are where this function is going to change sign. So what I should probably do is break this into, you know, the integral from 1 to 2. Plus the integral from 2 to 3. Because if the absolute value is going to change signs, it has to change signs at one of the places where the function is equal to 0. Okay. Now what you could do is the following. So now, based off of this graph, I know that on this interval, the function is negative. Right? Which means you would drop the absolute values and put minus signs in front of everything. And on this, it's positive. Okay. Now, if you couldn't do that just by looking at it, because let's say you couldn't graph it, you could create a chart. Right? So x between 1 and 2, and then x greater than 2. And if you do this, you get positive. What do I want here? X minus 1, so this is positive. This is also positive. This is negative. This is positive. And so the function is negative here and it's positive here, right? So you could do it like that. Or finally, let me show you like the worst way you could do this, but like it totally works. The answer is just to be like, I actually don't know. Is this function positive or negative here? Well, let's just drop the absolute values and compute an integral and see what we get. So the integral from 1 to 2 x cubed minus 3x squared plus 2x dx. Right, so that's going to be 1/4 x to the 4 minus x cubed plus x squared from 1 to 2. And if I plug all that in, what do I get? So 2 to the 4 is 16/4 minus 8 plus 4 minus 1/4 minus 1 plus 1. This thing, this is 0. And then this, so I just get negative 1/4, right? Right, exactly, yeah. So as sort of like, so x less than 0 would be something we would normally do. You're right, like if I was actually worried about it, but the integral is only from 1 to 3, right? So if you want to include x, like, but x between 0 and 1, you can totally do that. It's just, it's not necessary for this question because the question only wants to know what happens between 1 and 3 here, right? So you can kind of, you're not worried about what happens at 0. So if you had no idea whether this function was positive or negative, what you could do is you could compute the integral. And if the integral you get is positive, great. The answer, the function was positive. And if the function is negative, well, you say, okay, I screwed up. I should have taken the negative of this. And you'd say something like, oops, I should have used the negative. So, right, because we know this answer has to be positive. And so if you compute it without the absolute value and you get a negative answer, well, then that should have been positive 1/4. Do you know what I mean? I mean, I could, so be careful with your inequalities, right? You want 2 less than x less than 3. And yes, I could have done that. On the other hand, again, like 3 is the last point. So I'm not worried about it. Like after this point, the function doesn't change signs anymore, right? It just keeps shooting off to infinity. The reason why I put the 1 here is this function actually does switch signs again here. So if I were to just say x less than 2 here, strictly speaking, that would actually be incorrect. Like my table would not be okay. So it's just sort of like a pedantic thing. If you're not certain, like when you should include things and when you shouldn't, just include them all, right? Like it's usually not that much extra work. So I got a direct message, can we just do them in parts? And then if the answer is negative, then inverse it, yes. However, I want you to include, if you do it and you screw up, don't redo it, okay? That's a waste of time. I don't want you to do that. But what I want you to do is include something like this, okay? It doesn't have to be informal as what I said, but what I want you to do is to acknowledge, I screwed up here, but I recognize that instead of redoing the work, I'm just gonna flip the sign. That is totally okay, but I want you to write that down. Don't just, not write this and then like make me somehow guess that you got to this, right? Give me some sort of explanation saying, yep, I screwed up. I identified that I screwed up, but I know how to fix it. And this is the correct answer. And that's full marks. There's no deduction there, right? I love that you can say, I understand what I'm doing well enough to identify when I've made a mistake, right? To validate your own mistakes. And then know how to fix them. And for me, that's phenomenal. Like hell, if anything, that should be bonus marks. You shouldn't be deducted for that, but you got to put that line there. Otherwise, you're not signaling that to me. You're just doing magic. Okay, so that's sort of the idea there. Yeah, can you put a minus sign in front of the integral? That's absolutely actually what you normally would do, right? So if you knew ahead of time that the function was actually negative on this interval, you would say, oh, well, this integral then is the integral from 1 to 2 of negative x cubed minus 3x squared plus 2x, right? That's what happens when you drop the absolute value sign. If your function inside the absolute values is negative, then when you drop the absolute value sign, you have to put the extra minus sign in there. And then if you want to take this thing out front, that's totally cool as well. Right? So all of those are totally valid. Like there's a bunch of different ways of doing them. This is why though, because there's so many different ways that you can sort of parse this and evaluate this, again, including some sort of written explanation, even if it's just, a couple of words, really, really helpful to whoever's marking so they understand what it is you were trying to do, what technique you used. And we know that you didn't just do magic, right? Like we can see what you were trying to do. Yeah, absolutely. Yeah, Terrace, that is a beautiful explanation. Like that is absolutely a phenomenal way of writing it down. And yeah, and then in that case, you're not even admitting you made a mistake. You're just saying like, oh yeah, I computed it, whatever. But it's beneath the x-axis, so I know I actually have to, make it positive so that it was the same if I had done it above the x-axis. That's a totally great explanation as well. Absolutely. Okay, right. So if you go through and you do this, so you get positive a quarter for this half. So the answer is D, right? It's 5 halves. So you have to go and you have to now do 2 to 3. Now it's positive here, right? So you can just drop the absolute values and you get sort of the same thing, right? You get 1/4 x to the 4 minus x cubed plus x squared from 2 to 3. So this is going to be what? 81/4 minus 27 plus 18 minus, we already computed this thing. This thing's 0. Okay, and this thing here, so this is negative 18. So if you make everything over 4, you're going to get what? So you get 81 minus 72/4. So that's what, 9/4? Did I screw that up? No, yeah, that's right. And then you have to add these two things up, right? So you get 9/4 plus 1/4. So that's 10/4. And that's 5 halves. Okay, so the final answer is 5 halves. Okay. Okay, exercise 9.4. Sure, I see that. So does that make sense, everyone? Do you see like how you do that? And why it was so critical. And again, it doesn't matter. Even if you can't see what the graph of this thing looks like, you got to find the roots of your function, right? Because if you know the roots of your function, you can break it into parts between each of the roots and use that in order to figure out, oh, I computed a negative, let's make it positive. And then if you just break it into each of those parts and add them all up at the end, you'll get your right answer. All right, so even if you can't see it, you're good. A11Q3. Okay, so if everyone's good about this one and they don't have anything else, we can transition here into like office hours. Yeah, sure. Here, let me just maybe zoom out a bit there, and then like that. Yeah, that's great autocorrect. I like it. Okay. Everyone's good? This is your last chance for this. Otherwise, I'm going to get an office hours because I got a nice, queue of questions lining up here. People want me to take up, so. Yeah, sure. Actually, somebody asked that exact thing. Christian, was it you? No, I don't think it was you, but somebody asked the exact same thing. So we can do that. That's not a big deal. And I imagine, so yeah, one of the things that I've been asked to do is like 828, 829. And I imagine probably because it's similar to what's in the assignment, right? So let me just pull some stuff up here. Give me a second. And I just want to make sure I'm not giving something that is exactly the same as assignment 11. Wait, we didn't use the exact same function, did we? No, it's different. Okay, cool. All right, so yeah, first things first was like 828 and 829. Now I might not do them all, but just enough to get you guys comfortable with doing some of the others, and then you can try them on your own. And then again, you can come back and say, hey, I didn't understand how to do this. So let's look at, which one do we want to do? I think 829 is probably, well, let's do a little bit of each. Okay, so we're looking at exercise 828. And yeah, office hours recorded for sure. So 828 now, is there one in particular that anyone wants me to do from 828? Like A is, you just kind of have to do it. There isn't sort of anything nice about it. I really wish I could just copy. Hold on, let me see if I can get my keyboard to work. I don't want to draw these graphs, and it's really ticking me off that my stupid thing isn't working. So just give me a second here. Is it Zoom? Is Zoom breaking it? Where the heck are my notes? All right, I'm just going to download them onto this computer. Well, like I said, let me do one or two just to kind of get you into the, like B is actually straight. B is straightforward. Does anyone know how to do B? Can anyone explain it? Blah, 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 blah. Let's go. Okay, cool. And then 8. Okay, now you better work, you stupid thing. Aha! I don't know why it didn't work before, but I got it to work now. So just give me a second here. I'm just going to copy and paste the graphs in. And all right, sweet. I'm going to reshare now. Yeah, so 828. And so the reason, right, you can see we're going to use that one later. So let's not worry about that. And then I'm going to make this one really big, right? Because we want to be able to see it. Okay, so this is for 828. And the first one says, find the integral from -2 to 0 of f of x minus g of x dx, right? Yeah, exactly. Yeah. Yeah, the antiderivative of capital F prime, or sorry, F prime and G prime are F and G. And so you can just plug those in now and you've got your answer, right? So we can talk about that in a second. Here, let me do this. So wait a second, now I'm confused. Given the graphs of F and G in the figure below, oh yeah, -2 to 0, okay. So, right, we're looking between here and here. So we don't care about the graph anywhere else. We're just kind of looking in here. And we want to figure out f of x minus g of x. So what we're looking for is this area, right? But the area between the two functions here, this area, and then this area as well. And there's a nice little hint, there's a nice little trick here. Notice that these two areas are negative of one another. Do you guys see this? So the sum of these areas, this is 0. And you don't have to break it up like this, but I'm doing it because it's so nice, right? Because this here is 0. Is everyone okay? Tell me, because I'm certain somebody here is not okay with this. Why is that? Everyone's all right with that integral being 0? Okay. Okay, yeah, I knew there was a no. Look at the functions, right? The red function is right here. And the area between the red and the black, here, let me maybe like draw arrows, is this, right? So do you agree that the area between -2 and -1.5 is the area I've shaded it, right? Okay, now the area between -1.5 and -1 is the exact same thing, but this time the red function is on the bottom instead of being on the top, right? So on the left-hand side, the red function was on the top and the black function was on the bottom. On the right-hand side, the red function is on the bottom and the black function is on the top. So you get the exact same area, but because the functions have switched, that means that the area you're going to compute is actually negative. And so the areas that you compute, they cancel one another out. Now, if you want, you can actually try like writing down these functions. Okay, these are just straight lines, so you can write them down and you can compute this if you want. But really, the advantage here is being able to look at these two things and say, look, these two things cancel out and they give me an area of 0. Okay, so does that help? Like, do you see why one is the negative sign of the other? Like the fact that the red function, right? Like the red function is g and the black function is f. So f minus g, maybe if I zoom in a little bit more. So on this interval, if we look at f minus g, that's going to be less than 0, right? Because the black function is beneath the red function. So f minus g is less than 0. On this interval, f minus g is greater than 0. Right? But they both give you the exact same areas, but their signs are different. So that means that they cancel out and they just give you 0. Okay, cool. So the only thing that's left then is I just need this area. Right? Again, the area between the two functions. And well, what is that? Well, this is a rectangle, right? So yeah, exactly. It's 2 times 1. So the answer is 2. Okay. So that's A. Any questions about that? Okay. Now I'm going to do, like, I'm going to write things in a slightly weird way. Okay. I'm going to actually like now do B up here, just so that I can keep the graph around, you know what I mean? Okay. All right, so B says, and again, it was kind of pointed out that we can just anti-differentiate this. So it says find the integral of -3 to -2 f prime of x minus g prime of x dx. And it was pointed out that we know an antiderivative of little f prime minus little g prime, right? And that's f of x minus g of x evaluated from -3 to -2, right? And we just plug everything in. We get f of -2 minus g of -2 minus f of -3 minus g of -3. And you can work out what these numbers are. So f of -2 is where? F of -2 is this number, and f of -3 is 0. So f of -2, this is equal to 0, and f of that's -1. This number here is 0. As for g of -2 is +1, and g of -3 is -1, right? So we're going to get -1 minus 1 minus 0 minus -1. And be careful with your minus signs because there's a whole bunch of minus signs here. -1, so that is -3. Can I color the 2 by 1? Sure. So from part A, this is the 2 by 1. G of -2 is positive. Yeah. So G of -2 is right here, right? Here's -2. This is G of -2, right? And what is the Y value of that? Is 1. Same, yeah, let me answer that one in a question. I'm still, okay, and you're good? That makes sense? Okay, cool. Simon, absolutely, you could use linearity right from the get-go. That's a great way of doing things. So I think in that case, what you're saying is write this as the integral from -3 to -2 f prime, like this. Is this what you mean? And then do each of those separately? Yeah, totally. Absolutely, you could do that. That's a great way of doing it as well, right? You get f of -2 minus f of -3, or yeah, I mean, like, you can see that you get the same answer, right? You just kind of like, that is this, just written in a slightly different way, but totally, yeah, absolutely, this gives you the same answer. So yeah, very nice. Now, legitimately, when we had students do this in the test, you know what they did? There were students who wrote this entire function, like they figured out what these functions were, right? They wrote them as like these big piecewise things, and then would compute their derivatives or go and compute their integrals. And you can see, like, we didn't want students to do that, right? Like, we wanted students to just look at these things and be able to, like, if you understood what you were doing in terms of the integral, you could just sort of look at the answer and get it. But students would go through when we marked this, and we're actually writing the entire functions down. And you can imagine we're not going to make you do something like that, right? If something is big and ugly like this, that's not our goal. And so there's probably a better way of doing it. Now you can do it that way, and it's totally fine, and it does work out. You'll get a correct answer. But I promise you, most of those students made an arithmetic mistake somewhere, which ended up really screwing them up, right? So don't try and make things more complicated than you have to. Yeah, you could have used linearity here for part A as well. Like, totally, you could do this for part A. Like, there's no reason not to. And it's not it's like anything, right? Like, if it's a legal rule, you're allowed to use it. So it's not a coincidence here. It's just a different way of doing it, right? Just like when we were doing differentiation, I said, hey, if you use different rules, that's totally okay, as long as you were allowed to use those rules. Linearity is a legal rule. If you want to use it, go crazy, right? And in fact, I don't think it makes it any, like, these two solutions are roughly the same length, like using linearity at the beginning or not. So, it's just down to personal preference at that point. Like, it doesn't, you just do whatever makes you happier. But yeah, linearity is totally cool. In fact, I probably would have done that personally using linearity, but for a teaching reason, I kind of want to show people using antiderivatives. Yeah, so that's fine. Now, C, so the interval is -2 and -3. Yes, yeah, right? Because that's what the question gave us right here, was -3 to -2. And that's why those numbers came in. All right, now C, this is a beauty one. So C asks you to do the following. Now this one, like, again, if you're trying to do this by writing out what f of x is, you're just gonna die, right? You don't want to do this way. It is possible, but don't do it. Like this. Okay. If 2 boxes is 2y. Yeah, okay, so Jeremiah, you're fine? Or do you need me to clarify something? Okay, you're good? And Brandon, exactly, yeah, this is, okay, perfect. This is substitution. Brandon, what's the substitution we should do? Great. I would do a little bit different. I mean, you can do that if you want. I'm going to put the +1 in there, okay? Just because, again, if you can make that go away, then it's going to make your life a little bit easier, right? And it doesn't change du at all. So I'm just going to throw that in there, and you should totally feel free to do that as well, right? Yeah, totally. So now remember, technically when you do a substitution, we have to change the bounds of integration as well. So I have to figure out, now this might be a good one to not to just change everything back to x's when you're done. But if you wanted to do it with changing the bounds, what would you do? So we need to figure out what u of -5 is. So that's f of -5 plus 1. F of -5 is 0, so that's just 1. And then we get u of -1 is f of -1 plus 1. F of -1 is 1, so this looks like it's 2. Does everyone see what I did there? Like how I got those numbers? Okay, cool. So now we're going to do our substitution. So I'm going to get the integral from 1 to 2 of the square root of u du. And what is that? So that's u to the 1/2. So I'm going to get 3/2. So I'm going to get 2/3 u to the 3/2 evaluated from 1 to 2. So that's going to give me 2/3 times the square root of 8 minus 1. Right, yeah. Substitution is another way of finding an antiderivative. Absolutely it is. Now the benefit here though, right, is when if you do this step where you actually evaluate what the bounds are, then the benefit of doing this is that you don't actually have to compute what the antiderivative is, right? When you do substitution and you do it in an indefinite integral, you're really just finding an antiderivative, right? That's what substitution is winning for you. But if you change the bounds of integration, then you don't actually need to find the antiderivative. That's sort of a nice thing that happens with substitution that doesn't necessarily happen anywhere else. So this is why we might change the bounds. But if you're not comfortable doing that, you can kind of, just find an antiderivative first and then evaluate this thing. Doing that, that's totally fine as well. So those are all perfectly great ways of doing this. Okay, everyone good on that? Okay, I'm going to assume yes. Just again, scream at me though if something there doesn't make sense. Now I'm going to move this down because this is the graph for 29. I was asked for that one as well. Oops. All right. So this is the graph for 829. All right, so I don't want to do all of these ones because they're all sort of like very similar. And I think, in fact, some of them are very similar to what is in the problem. Yeah, so let's see. So let's do, sure. Sure, that's different enough. Let's do B. Okay, let's do B. You have convinced me. Okay, so B is the following. So it says find the integral, or here, maybe I should, for anyone who doesn't have this, maybe let me just define what capital F and capital G are. So capital F is the integral from 0 to x, f of t dt. G of x is the integral from 0 to x, g of t dt. All right, so again, very similar to the last problem is we're taking up the integrals, right? We're looking at the areas under the functions. So we're going to do B here. And B says to do the following. So this is the integral from 4 to 5 g f of x, f prime of x dx, right? Okay, what do you guys think we should do? Anyone see like an obvious integration technique? Substitution again, cool. What substitution are we doing? Maybe I should make this smaller. Ooh, there we go. Great. So let's right? Because remember, when you're doing substitution, you're looking for the presence of a function and its derivative. And here it's really spelled out for you, right? Because you can see a function and its derivative. You see an f of x and an f prime of x. So let's let u be f of x, du be f prime of x dx. And again, if we want to change the bounds, we can do that. So u of 4 is the same thing as just f of 4. All right, which one's f? F is the black one. This one maybe not great, right? because this is like a weird thing. This looks like it's 2.5 or something. So maybe let's just leave it as this for now, right? Like, let's not worry about it. You still have to change what's written. Is f of 5 any better? F of 5 is nicer, but let's just leave it as f of 4 and f of 5, right? Sure. Well, let's see what happens. So Saeed, if you don't know whether you can do it, an easy thing that you can do is just try it. And if it doesn't work out, well, it wasn't meant to be. But if it does work out, phenomenal. So you remember, everyone, when I say, like, if you don't want to change the bounds, you still have to write something in that spot, but you can just kind of change back afterwards. So let me do it like this, right? So you see, these are just placeholders. Like, I don't, I know what the numbers for these are, but let's just leave them here as placeholders. And I'm going to be left over with this thing, g of u du, right? Okay. And what is this problem asking me to do? I guess I actually do need to do these, don't I? Dang it. So f of 4 is 2.5. F of 5 is equal to what, 2? So I guess I actually do have to do these. This isn't a one where it's going to be easy to do. Okay. So now at this point, you'd be like, okay, what the heck do I do now? But look at the question. It's saying find the area under the function g between 2 and 2.5. Okay. Well, let's look at the graph. So between 2 and 2.5, this is what we get. Oh, sorry, this should actually be the other way. It should be 2.5 on the bottom. Right? So this is going to be negative the integral from 2 to 2.5. And that's just going to be equal to 1. Yeah. Yeah, thanks, Agam. Yeah, I caught it before I saw your message, but I'm glad that you're keeping me honest. And Brandon, exactly, it's half that length, right? The width is just a half, the height is 2, so 1/2 times 2 is equal to 1. And there we go. Does that make sense, everyone? Why is it negative? Okay, look at the bounds. Right? I've got 2.5 on the bottom, and like, I don't want the bigger number to be in the bottom, right? You always, usually when you're actually trying to compute an integral, yeah, exactly. You want the bigger number to be on top. So what I'm going to do is I'm going to flip these guys around. But when I do that, it comes with a price, right? And that price is that I have to throw that minus sign in front. So that's what I did. That's where the minus sign came in. I put the minus sign in front, but then I get to flip the bounds of integration. And now I'm in a position where I can actually compute this pretty handily because I just look at the graph and I examine what it is from the graph. Okay, cool. Sure. I mean, like, we can do it mathematically if you want. It's just that here it actually kind of makes your life worse. So we're interested in the function. Here, let me kind of draw it between here and here, right? So what is g of x on this space? So g of x is just the constant function 2 on the interval to 2.5, right? So the negative integral from 2 to 2.5 of g of u du is the negative integral from 2 to 2.5 of 2 du. We know that we have negative 2u from 2 to 2.5. So that's negative 2 times 2.5 minus 0.5, or sorry, minus 2, which is negative 2 times 0.5 equals negative 1. Sorry, yeah, that should be negative 1. Yeah, but you see, it's actually like more work than like just, if you look at the graph here, you say, oh, okay, there it is. Yeah, exactly. It's negative just because before, right, when I switched those bounds of integration, I had to throw that minus sign in front. And then once I have the bounds in the correct order, where the lower numbers on the bottom, the bigger numbers on the top, then I can look at the graph, right? If you have the bigger number on the bottom and the smaller number on top, you could look at the graph, but you have to remember that your answer is like you've gotten the negative of your answer, right? So really, if you want to be able to look at the graph, make sure that your smaller numbers on the bottom, your bigger numbers on the top. Like graphically, this thing here, this thing in the blue brackets, that's equal to 1, right? I got that from the graph. That's right. And then the minus sign just came from the little bit of algebra of flipping the bounds. How can we find like the big function f? I mean, generally, I mean, you could if you really wanted to, because everything here is straight lines, right? So you could compute what the equations of each of these lines are, and then you could actually go ahead and like run through the computations. But generally, you don't want to do this. And in none of these questions are you required to do that. So, you know, don't. Like, for example, in A, you know, without me sort of like going into it, part A, you should integrate by parts, and you should differentiate the function capital F. Do you know what I'm saying? So without me doing it, right, part A, you have, you know, an integral from 2 to 3, f of x. You should integrate by parts. And in doing so, you can differentiate this thing, right? And you know that the derivative of capital F is little f. And so that's great because that's going to make your life really easy, right? So you can effectively, everywhere that capital F and capital G appear, if you use integration by parts, you can manage to make it disappear, right? And that's sort of like the key to this problem. Okay, so give that a shot. See if you can work it out. Okay, so next, you could do U sub. Sort of the only thing that you're worried about there is if you do U sub, is your answer is probably going to be in terms of capital F. Do you know what I mean? So the natural thing to do here is to say something like if you were to do substitution, say let U be f of x, right? So du is little f of x dx. And then when you do this integral, right, you would get f of 2, f of 3 of what? Of u du, which is okay, right? This isn't terrible. So you're going to get 1/2 f 3 squared. Yeah, so you could do it this way as well. Yeah, it totally works out. But you do have to then go and compute these things, right? So you would have to compute what f of 3 and f of 2 are, which are, you know, they're not impossible by any means. But you would have to compute them. And are there some questions where you have to use both? Absolutely, there are. Yeah. Yeah, unavoidably, there are definitely questions. In fact, do I still have it up? So from week 8, there's a week 8 problem that's up, right? And these poll questions have been posted, so you guys can go check those out. Which one is it? This one. Okay, so this is the, oh, shoot, sorry, I'm not sharing my whole screen anymore. I'm just sharing my thing. So hold on, share my whole screen. There you go. So in the week 8 poll questions, so question 11 here is this bad boy right here, x to the 5 e to the x squared. This requires both a substitution and an integration by parts. Now, in theory, it is actually possible just to do it as an integration by parts, but it's like you'd have to be quite clever to see what the integration by parts is. So it's much easier to do as a substitution first and then an integration by parts. So this is a really good one to practice if you want something that uses both. That, unfortunately, is mostly practice, right? Like is figuring out which method to use. But as a general rule, you should try to do substitution first. And then if substitution doesn't work, then you try integration by parts. So Ariana, what are you suggesting? Like the substitution? I would do x squared. Now you can try x cubed and see what happens. The reason why you don't want to use x cubed is up here, right? Because you probably said, oh, I see an x squared here, right? And so if you differentiate the x squared, that's great. But the problem is you don't want the du to be in an exponent, right? Like that's really bad. The du kind of has to be out front with everything else. So when I look at this, I say, oh, that x squared in the exponent of e is really ugly. Like I don't like e to the x squared. In fact, I know that function is really hard to differentiate. So I'm going to substitute away the x squared, right? So I'm going to let u be x squared and then rewrite this thing sort of as appropriate, right? And the derivative of x squared is just x basically. So what happens? Well, here you've got 5 x's. You need to keep one of them for the substitution, and then the other 4, well, that's just u squared, right? If that makes sense, give it a try. Yeah, sure. So that was the next one I was going to do. So 9-4 is next in my list. Let me just pull it up. All right, 9-4. Ooh, okay, yeah. So 9-4, find the number c such that the line y equals c divides that region. So this is exercise 9-4. Find c such that y equals c divides y equals x squared into 2 subregions of equal length. Okay. So let's begin by drawing our region, right? And so this here will be -2. This here will be +2. And the region bounded by x squared and y equals 4. Okay, so that's this region right here. Okay, so the question is, what we want to do is we want to find the point C such that if I draw this line across, then I get an equal amount of area above the blue line and an equal amount of area beneath the blue line. Okay, so that's our goal, is to do that. Now, the first thing I should probably do is figure out what that area is, right? Because that's definitely, like, if I know what that area is, then at least I know sort of what my goal is. So let's find that area first. So that's 4 minus x squared dx. Does everyone agree? Okay, great. And if I do that, what am I going to get? So I'm actually, let me cheat. I'm going to write this as the integral from 0 to 4 minus x squared dx. That's just a little bit easier. So that's going to give me 4x minus 1/3 x cubed from 0 to 2. So it's going to give me 2 times 8 minus 8/3. And what is 8 minus 8/3? 16/3. So I'm going to get 32/3 here, like that. Okay, so far so good. All right. So now I'm going to choose, I'm going to say, like, let y equal c, just be some, arbitrary line. I don't know what it is. But basically, I want to make sure that the area under this line is equal to 32/3. Okay, so I've got my line y equals c here, and I want this area to be 32/3, right? You could do either, right? So you could let this area be 32/3. It doesn't matter, right? Because you want them both to be the same. Or sorry, half of 32/3, so 32/6. So in that case, what I was doing when I did that too, I said, look, it's the same as, yeah, you're right. So it's, instead of 32/3, it should be 16/3. But that 2 came from me saying, like, look, the area from 0 to 2, like the whole area is just twice this area. right? Like just by inspection. And if you don't want to do that, don't worry about it. But I can just look at this and say like, yeah, if I like just compute the area from 0 to 2 and then double it, that's the whole area. Okay, so we want the blue area or the green area to be 16/3. Turns out way easier to compute the blue area. So let's compute the blue area. So the first thing that we have to do is say, oh, okay, where are we integrating from? So what are these 2 points here? Okay, so I've got to integrate from something to something. Something dx has to be 16/3. So what are my bounds of integration? Square root c, great. Plus and minus root c. Does everyone agree? Does that make sense? Yes, yeah. So Jeremiah, we're looking for the place where it's exactly half. So exactly half of 32/3 is 16/3, right? So exactly equal. Is everyone good with plus or minus root c? Because this is important, right? Like why is it that? Okay, see assignment. So the reason why it's root c is, so if we zoom in on this, again, this is the line y equals c, right? The blue line is y equals c. And this is the equation y is equal to x squared. So if I solve the equation c is equal to x squared, right? Because the y value here is c. If I solve the equation c is equal to x squared, I get plus or minus root c. And that tells me what my x value is at these points. Okay, sweet. All right, and what's the function? So what function am I integrating? Perfect, c minus x squared. Okay, so this has to be equal to 16/3. And if we do this, what are we going to get? So let me do the same trick. Integral from 0 to root c, c minus x squared dx. So that's going to be 2 times cx minus 1/3 x cubed from 0 to root c. So that's going to be 2c root c minus 1/3 c root c. So that's what? So that's going to be 2 minus 1/3 is 5/3. That has to be equal to 16/3, and now you can solve that for c. Yeah, exactly. Yeah, c minus x squared, because we're trying to find the blue area. So we're going to look at the top function, and we're going to subtract the bottom function, and that gives us the blue area. Why is it 0? Like which thing? Like why is this 0? Same thing I did above, right? Which is to say, look, hey, if I want this, the blue area, I can just compute the black area and multiply it by 2. So I compute the area from 0 to root c and then double it. Again, you guys don't have to do that if you want. If you want to keep in the negative root c and the root c, you can. But you can see like it's a little bit messy because it was really nice that I was able to plug in 0 into this. It made my expression really, really easy. And if I had to plug in root c instead, there's much more of an issue that you can make like some sort of silly computational mistake, right? So is that good? Does that make sense? C minus x squared? Okay. So I mean, like, here, let's zoom in on this again. And let me kind of get rid of a bunch of the extra fluff here. Okay, so we're after this area here. Do you agree? Right? Okay. So we, just like when we find the area between two curves, the top curve, this is the line y equals c, right? That's the top function. Here, maybe let me write this as like g of x equals c, right? And then this bottom function here, this is f of x equals x squared. So when I want to find the area between two curves, right, what do? We do the integral from the lower bound to the upper bound of g of x minus f of x. dx, right? And my upper function is just c. My lower function is x squared. And that's how we get that. Okay, cool. For numeracy 2, what's the role of t? Okay, let me pull that up. And what if we wanted to compute the area above? That's, Christian, this is a great question, but it wouldn't be x squared minus c. Yeah, it doesn't quite work out that way. So there isn't a super nice way of doing it. The way actually I would do it is to, and I, depending on the videos, you might not have gotten to this point yet, I would actually integrate this along the y-axis if I were to do it that way. Okay, so I don't know if you've seen that video yet, Christian, but if you haven't, go check it out about how to integrate along the y-axis. Exactly, and that's how I would actually do this, because doing this along an x-axis is actually a little bit too tricky. Yeah, this is a little bit nasty. Or if you were to do it, what I would do, is I would compute this black box, and then I would compute the blue area and subtract the blue area. And you can see that that gives you the right answer, right? And those blue areas you can compute, like those aren't too bad, but it's just computing this inside thing is actually surprisingly tricky. So I wouldn't try and do that directly. In this case, there's definitely one half of the shape is easier to compute than the other half. In numeracy 2, yeah, no problem. So I got this question, and then somebody wanted me to talk about numeracy 2 anyway. Let me do a numeracy 2. Actually, Curdy, did you ask about question 2? By that, you meant numeracy question 2, right? Okay, cool. Let me do a really simple example, everyone. So here's a function, f of xy equals x times y, okay? Sure. So here's a function. I've got the function f of x, y is equal to x times y, all right? And again, so my claim is that this function is homogeneous of order 2, okay? So what happens if I compute f of 1, 3? What number do I get at? What's the output of f1, 3? 3, perfect, exactly, okay. So now what I'm gonna do is I'm gonna multiply both of those numbers. Oh yeah, beautiful. There's lots of people who just a little slow on their 3s, but exactly, I love that you all got it. So now let me multiply every number inside of my function by, what do we want? 4? Let's multiply by 4. What do I get? 48. Notice that that's 4 squared times 3. Everyone agree? What would happen if I multiplied every number by 2? So I had to get 2, 6. That's 12. Notice that that's 2 squared times 3, right? Or, yeah, let's just leave it like that. Well, this doesn't prove that it's homogeneous for k is equal to 2. We have to kind of do it more in general, right? But yeah, here, let's try doing something else. So let's say I just let t now be an average number, and I multiplied 1 and 3 by t. What would I get? So I'd get t 3t. What do I get if I compute this? You'll see in a second why the square comes in. 3t squared. Or maybe let me write that as t squared times 3. Right? So what the t there is doing is just keeping track of whatever that number is. So how would we do this in general? So instead of like fixing 1 and 3, what is tx, ty? Great. Yeah. And notice that what is this thing right here? That's F. So does that make sense? So we've shown if you multiply, if I give you the function f of xy equals xy, then if you give me one number, like one pair of points that works, and I multiply both of those numbers by something else, but by the same number, then I don't have to recompute the entire function. All I have to do is multiply my first answer, f of 1, 3, by whatever t squared is, right? Right, exactly. So Brandon brings up a great point, which is, to show that a function is not homogeneous, all you have to do is give an example, okay? To prove it is homogeneous, you actually have to do what I just did here, right? Like you have to kind of do it in general. But if you want to show that something is not homogeneous, all you have to do is give a single example of where this identity would fail, right? And that's all you have to do. Okay, so does that clarify sort of like what you need to do for question 2? So Kelly, the definition of homogeneous is in the question, right? It's that f of t x1 ... t xn is t to the k fx1 xn. It's like you can pull the t's out sort of, but at the cost of putting some sort of power there. And you don't know what that power could be. It really could be anything. But your function is homogeneous if you can do this. And these functions, homogeneous functions, are super important mathematically, right? They show up a lot of the time. They're really important. Okay. Sure. So now let me just say this. So somebody asked, Curdy, I think it was you, about 11 question 1. Now we kind of did that when we were doing 28 and 29. So you're okay with that? Like when we were doing 828 and 829. Okay, cool. So it's really just question 3, I think, is the only question that's outstanding. Yeah, this is the important point. So people are like, where the hell do I even start with problem number 3? There's a really slick, easy answer to this one. I'm not going to tell you what it is. If you find it yourself, phenomenal. The entire point of nonlinear systems of equations is that they're hard as hell, and there's no algorithm for solving them, right? When we were doing linear algebra, we knew we could put things into a matrix, we could row reduce, we could do all those sorts of things. Nonlinear systems of equations are all completely different, and you have to solve them all completely from scratch. It depends on what you mean by brute force. What I would recommend doing is, let me see if there's something really nice that happens. What happens if you add equation 1 to equation 2 to equation 3? I want you to just add all 3 of these equations together. What do you get? That might not be a good one. Yeah, numeracy 3. So, okay, let's say this. What happens if you add equation 1 to equation 2? What do you get? Yes, Kelly, that's not a bad idea. Exactly. So, and this is a great point. Okay, phenomenal. So you notice how so I've got a bunch of direct messages, people give me the right answer. And do you notice that when you do that, the y variable disappeared? Right? You all agree? Right? Y disappeared? Jeremiah, you can basically do some sort of elimination. So remember, when we were solving linear systems, our goal were to sort of like combine equations in ways that made variables disappear. So now you've got this equation, 2x squared plus 3z squared equals 8. See if you can mess around with these equations in such a way that makes some of the variables disappear. And ideally, if you can get it so that there's only, if you add multiples of one equation to another, and you can get it down to a point where you just get x squared is equal to something, then you can solve for x, right? Yes, Jeremiah, I think that's what I got. But you don't need to ask me. You can just check, right, Jeremiah? Just plug your answers in and see if see if they work. Yeah, well then you don't need to ask me, right? You know the answers work. Okay, sure. So everyone, for the record, this is a relatively straightforward one, and I don't say that to make you feel bad. I don't say that to make you scared. I just want you to know that like the nonlinear systems of equations that we're going to start solving here are a nightmare. Are absolutely, and these are like relative. These are ones that can be solved. And my understanding is you guys have done Lagrange multipliers in econ. Like, have you seen those examples in economics? Yeah, Jack. Yeah, exactly. No, you guys didn't. I was always led to believe that you guys did some Lagrange multipliers in econ. Okay, maybe I'm wrong here. We're very going to quickly get to systems of 4 equations and 4 unknowns, and they are going to be super nonlinear, and we are going to have to solve them. And the economists are like, hey, yo, we use this all the time. We need you guys to do this. This is why we're doing it in this course. Otherwise, there's no way I would talk about Lagrange multipliers in 133, but I have been assured that it is super important in economics. And I know roughly why it shows up, right? But just to give you a heads up, you know, if you didn't like linear algebra, that was when the math was really, really nice. It's about to get much worse. And there's no algorithm. You just have to screw with stuff until something pops out. And I know that's not satisfying. That's somehow like the worst thing to hear. And trust me, I hated it too when I first learned how to do Lagrange multipliers and I had to solve nonlinear systems of equations. It's really unsatisfying to be told, just screw with it until something works. But the reality is that's largely true. And the more of them you solve, the better you'll get at solving them. But that's it. Yeah, in some sense, well, it depends on downhill. I usually use the expression downhill as in things are going to get easier, right? Like I would climb the hill and that was a lot of work, and then downhill things would get easier. But if you take downhill as things getting worse, then sure. But life is going to get worse, maybe, is just a more clear expression of what's going to happen. Okay, so yeah, give this one a shot and at least just start to get comfortable with these things. And then we'll, like I said, hey, listen, I know, because one of the things that I always get when we talk about this in Lagrange multipliers is like, how do I even know when I'm done, right? Like, how do I even know I found all the solutions? Because often, does anyone know? Actually, so who asked me was Jeremiah. How many answers did you get? Did you just get the one? Yeah, in numeracy 3. How many answers did you get? Okay, there's 8. All right, everyone. So numeracy 3 has 8 answers to it. But like, I think, right. So Jeremiah, like, you're just missing the obvious answers. Do you know what I mean? Like, write out your 3 for me and I'll show you a 4th. Oh yeah, you have to find all 8. 100% you have to find all 8. So Jeremiah, just write them as like, you know, number, comma, number, comma, number, and send all 3 to me and I'll give you another one. No, it's not that there's 8 x values, but there are 8 solutions, right? Because remember, even when we were talking about linear algebra, if 1, 2 is a solution and 1, 7 is a solution, those have the same x values, but they're different solutions, right? Okay, but Jeremiah, so what are your x values there? You could do that, Ariana. I'm just trying to get Jeremiah to send them to me in a direct message. Right, okay, so there's 2 possibilities. Now, I know that when you did y and z, you got 2 possibilities as well, right? So let's think about our basic counting theorem. You have 2 options for this one. You've got 2 options for this one. You've got 2 options for that one. How many options do you have? How many solutions are there? Do you see what I'm saying? No. basic counting, right? What do? You multiply them, right? Yeah. So there's 8 solutions because you have 2 options for what each of those things could be. Do you see what I'm saying? So I'm willing to bet, I'm pretty sure you have the numbers there. Like you have all 2 of the solutions for X, you have the 2 solutions for Y and the 2 solutions for Z, but you just haven't realized that they're all actually uncoupled from each other, that every solution, that there's a solution for every corresponding choice of X, and there's a solution for every corresponding choice of Y and every corresponding choice of Z. Do you know what I'm saying? Does that make sense? I can't tell if you're just typing along a reply. Right? Because it's static. So at least like in person, I can tell when people do. Well, because okay, so you've got 2 numbers for X, right? Like 3 and 7 or something. You've got 2 numbers here, 4 and 5, and you've got 2 numbers here, -1 and 0. Well, you can choose any of these 2, right? So you could have 3, 4, -1. You could have 3, 4, 0. You could have 3, 5, -1. You could have 3, 5, 0. You could have, you see what I'm saying? Yeah, so you have 8 solutions for that reason. Okay, good. Okay, cool. So everyone, you're going to get the same thing too, right? You're going to get 2 options for X, 2 options for Y, 2 options for Z. Turns out those answers are uncoupled from each other. You could choose any of the X's, any of the Y's, any of the Z's. They're all solutions. And it's not like you have to do 8 cases. That's not going to happen. You're going to be able to solve them all sort of simultaneously. It's just that 8 solutions are going to pop out. And you'll see what I'm saying once you actually manage to do it. It's not a lot of work. It's just that there are 8 answers. Okay. All right, everyone. No, don't worry about it. And Brandon, I don't think a lot of people do this stuff. Like this stuff is relatively new. Don't worry about it at all. Like 90% of the class didn't learn this stuff. Yeah. Yeah, it seems right, Kelly. That's definitely, I don't remember if X is exactly that number, but that is the right sort of thing that you should get. Yeah, no problem, Jeremiah. Yeah. All right, everyone, have a good Wednesday, and I'll see you Thursday evening. Okay, ciao.